OK, if it's possible, come closer, please, because I have one contest for you, and I have the prize for it. So I hope you see the slide like clear and good. So if don't, please come closer. OK, let's start then. Hello again. My name is Daniil, and I'm a software engineer in the Bolt Technologies company. You probably know our scooters, our bikes, and probably you already ride them here in Berlin. So my main responsibility is the car sharing stuff. It's the part of our application called Bolt Drive. Not yet launched in Berlin, but who knows, maybe sooner. And today we're going to dive into the DEX files, cover them byte by byte, and I will be your guide through this amazing journey. OK, so I have the following plan. We start with some introduction and notation. Then we will proceed to the DEX file structure itself. That's the main part, I guess, of the talk. And after that, we will cover the reasons of well-known 64K problem and what multi-DEX does with it. And also, in the end, we will compare the DEX versus jar to understand how the DEX file structure was developed. And here's our plan. OK, let's start with introduction and notation. So about the contest. So here's on the slide a honey badger. It's a smart, brave, and fearless animal. It's a Bolt mascot. So, and I would like to challenge you a little bit. I put a few badgers on my slides. So the task is easy. You have to count them. And in the end, you say the number. I say whether it's right or wrong. And if it's right, you get the nice Bolt hoodie. Don't miss the opportunity, guys. Including this one, yes, this is the first.
0, you mean?
Not 0. Don't mess me, please. It's the first one. Yes, we're going to cover the binary structure of file. Yes, it makes sense to count from 0, but like we're in the human world, not the binary world, so let's count from 1. This is the first honey badger. OK, let's start. And before we actually start, I'll give some disclaimer about this talk. So this talk was made out of my personal curiosity. I was curious about the things that I use in my work life, the instruments I use, and I believe that good engineer always curious and trying to understand how the things work under the hood, things that they use every day in the development. So I suppose we use DEX every day, not like directly, but indirectly we use it every day. So it's kind of edutainment talk, some part of education, some part of entertainment. So I don't expect that you would have some everyday benefit out of it. Just like maybe you got some insights from the talk, because the structure of DEX file is relatively complex, and I see some good decisions that engineers made when designing these formats. So I hope that some insights will be useful for you as well. And sorry, last point. Actually, I didn't cover whole DEX file. It's kind of large. It's going to take 3 hours to discuss it all. So I just keep some boring stuff and leave the most interesting things for you. So what is DEX? Actually, DEX stands for Dalvik executable. That's it. So this file contains executable code for Dalvik virtual machine, which is now called IRT, Android Runtime. And what do we do with it? You have your Java or Kotlin files in your project. You write some code every day. Then you compile this code. Actually, you're using the Java compiler for it. And as the output for this task, you have the class files, right? And after that, you pass those class files to the D8 tool, which compiles them, bundle them in one single DEX file. Not actually the single one, but like in many files in one DEX file. That's what's going on. That's how your code converted in the DEX file. And a few words about the notation. So we will be talking a lot about the offsets today. And so when I'm talking about the offset, in most cases, I mean amount of bytes from the beginning of the file to the sum section of this file. If I'm talking about another offset, I will notify you explicitly. By default, offsets are counted from the beginning of the file. And a few words about the NDNS. For those who are not aware what is this, NDNS is just the order or sequence of bytes in digital data in computer memory of file. And NDNS is primarily expressed as big endian or little endian. You might have heard these terms. And so let's imagine we have 32 bits integer value. And if we're talking about the big endian, so in big endian system, the most significant byte is stored in the smallest memory address. And the least significant byte of the integer is stored at the largest address. And the opposite to it, we have the little endian system, which stores the least significant byte in the smallest address position, and it looks like reversed from the big endian. So by default, all integers, all data types in DEX files stored in the little endian format. And about the data types themselves, we have on my slides bytes, signed and unsigned, shorts, signed and unsigned, integers, signed and unsigned, and also special format called LAB or lab. I don't even know how to correctly pronounce it. I will call it lab. So lab 128 is little endian base 128 format, which is variable length code compression used to store arbitrarily large integers in the smallest possible number of bytes. So let's see a few examples. If you have to store some value in the range from 0 to 127, it's enough to use 7 bits. And in this case, the most significant bit will be set to 0, meaning that this is the last and the only byte in the sequence. But if you have a slightly larger number that requires 14 bits to store it, so you might use 2 bytes. And in this case, the most significant bit set to 1 means that this is not the last byte in the sequence. You need to read further until you meet the 0 in the most significant byte. So you can encode any amount of bytes in this way. It's similar how UTF-8 works, but actually Dalvik only use sequences up to 4 bytes. And the main reason here, the crucial thing, is that to save the space, because back in the days, Android devices have a low amount of memory, and every saved byte means that you not overload the RAM memory of the device when you start the application and all this DEX file in the memory. Okay, let's finally dive into the format itself. So basically, from the first glance, DEX file consists of 4 sections. Header, and the section which holds different identifiers and definitions. The biggest section is data section. And in the end, we have the link data section. But I'm going to omit this in this talk because the format of this section is not specified by documentation. It's only used for statically linked DEX files, and the format of it runtime implementation dependent. So nothing to talk about it. And let's start with header. Header have a bunch of different fields, and let's cover them one by one. That's why we're here. Every DEX file starts with the magic. Magic is just 8-byte sequence of bytes that can be treated like ASCII characters. The first three characters is DEX, which means DEX. After we have the line break symbol, and after that we have three characters which denotes the version, the format version on this file. In this case, it's the version number 39. And the end, we have the 0, which means this is a zero-terminated strings, and it allows some kind of file of managers or other programs which are not familiar with this format, read it like a plain, old-style C zero-terminated string, and at least get some meaningful information from the file itself, even if you don't understand the format. Okay, then we have the checksum of the whole file, except two fields, and we have SHA-1 signature of the file, except three first fields. Also, we have the file size here. I don't know why, but just in case, why not? And we have the header size here. Despite the header size is being fixed, it's anyway presented here, which allows introducing future extensions of the header by just changing the size of the header. And we have the endian tag here, and this tag is indicate the endianness of the file. And it has two possible values presented on the slide. As I said, the DEX by default is little endian, but implementations might choose to override it and use byte swapping in this case. Also, we have the size and offset of the link section. I will also go into omit this because it's for statically linked DEX files. I almost never meet them, so nothing to talk about here. And here we have the offset to the special structure called map, which is, in fact, contains almost the same information as the header. Even documentation say it has redundant information, duplicated information, so I will also omit it here because we will cover the header at all. And then the header has a bunch of pairs like size and offsets to the following sections of the file. First, there comes the strings section, then types section, prototype section, field section, method section of the file, class definition section, and we have the size and the offset to this large data section where all the raw data is stored. Okay, let's start with strings then. What is a must to say here? Every possible string that you can meet in a DEX file actually placed here in one single table. It allows DEX structure just have the index in this string instead of keeping the whole string in place in the structure, for sake of the memory saving, of course. And here comes the main idea, as far as I see it, of the DEX file. It's about deduplication. So instead of having the same entities here and there multiple times, we just put them in the dedicated table and then only operate with indices inside this table. That's how the duplication works, and we can save a lot of memory in this case. Okay, and the header has the size of this table and offset to it, I mean the string table. And the table itself is placed in a section where identifiers and definitions are kept. So header is colored with green color, and this identifiers and definition section is colored with like silk or I don't know, like bluish one. Sorry? Okay, yes. And if we have a look at this strings IDs table, every item in this table is also an offset, but an offset to the data section where strings value are actually kept. So let's have a brief look at this string data item structure. It has the size in characters, not the bytes, but in characters. This value we also get when we call string.length, we get the same value. And here we have the data itself. It's the sequence of byte encoded in MUTF, MUTF-8. UTF-8 is almost the same as UTF-8 encoding, but with a few minor exceptions. The UTF-8 uses only 1, 2, or 3 byte encodings, so 4-byte encodings aren't used. And the code point of 0 is encoded in 2-byte form, and the strings always ends with 0, like a C, zero-terminated strings. Okay, next section is types. Type IDs I also referenced from the header by the offset and amount of entries in this table. And every type in this table is just an index in the string IDs table, which we're already familiar with. So the type is a string description of it. And you can call it descriptor. So type is a string descriptor, that's it. But you might have noticed the weird format of these descriptions. But if you have ever worked with GNI, which stands for Java Native Interface, then you may see that these types are familiar to you. But if you haven't heard about this, so here's a table for you, just have a look, pretty simple. B byte, C char, S short, J long, just because. Okay, that's how the type descriptor looks like. Protos, or prototypes, the next section. As well as strings and types, all prototypes are kept in a single table. The offset and size are also in the header. And what is prototype, actually? What is it? Actually, you can treat it as a method signature, but without the name and visibility and other modifiers. So it contains only return type of the function and type of its arguments in the order. So that's the structure is for. It has the first field, and shorty is just a short description of the prototype, denoting the return type and type argument types expressed in concise type descriptor format. Then we have return type, which is also an index in the type IDs table. And we have the parameter of set. And arguments are expressed as an offset to a special type list structure, which is placed inside the data section. And this structure has a field, which is responsible for the types, amount of types inside it. And then we just have an array of indices pointing in the already familiar type IDs table. So this is type list. We'll just have the indices to types. That's how the types of arguments of function is encoded here. More high-level stuff, fields. What is field ID item? So let's see on its structure. First of all, it has the class index. It's the index and type ID section which denotes the definer class, the class which contains this particular field. Also, this structure has type index, which denotes the type of the field itself. And also it has the index in string ID section, which denotes the name of the field. That's it, easy. And we have methods, and we have fields, and we have methods in class. So the structure here almost the same. We also have the size and the offset in the header, which points to this table. And you might notice that structure is almost the same to the corresponding field structure, with only one exception, that instead of field type, we have the prototype provided as an index inside the proto IDs table. And finally, we can define the classes. We already know about the prototypes, we already know about fields, methods, types, strings, and now we can define the class in a whole. As many other tables, class definition table is also referenced from the header, which has its offset and size. There are many fields, but all of them deserve to be discussed. First of all, we have the index in the type IDs table, which describes the type of this particular class. Also, we have the access flags here. So some of them are presented in the table. So whether it's class public or private, is it interface or abstract class, is it enum or annotation class, you got it. Also, every class in Java must have the parent class, except the object. So this superclass IDX is the field which is an index in type ID section, which denotes the superclass of this particular class. And for the object, there is a special no index value placed there, marking this class not having a superclass. Also, class might implement some interfaces, and they are also placed here. And here's the offset to the type list structure we are already familiar with, because we had this structure previously when we were discussing the prototypes. So, the same. If you had compiled your DEX file with the -- debug option, that you would see the name of the file which this class belongs. This information might be used by debugger or by you if you're observing this file in hex editor somewhere. And if there is no such information, the special no index value is written in this field. Annotation offset is an offset to relatively large hierarchy of other structures. I don't want to get you bored to death, so I'm just briefly explain things that excite me the most from this structure. But in the end, all these complex structures are intended to express name-value pair, defining the arguments of the annotations. And the same we have here. The only purpose of the structure referenced by this field is to keep a value of static fields of the class. And in the end, after referencing a lot of structures, we come to encoded value structure. And what encoded value structure is? Let's have a look inside it. First of all, in the first byte, two things are encoded. 5 bits are taken by the value type, and the rest bits denote the number of bytes required to hold the value of this specified type. So type might be one of the following. There are primitive types and some other reference types, but the one interesting thing here is the array type. So the array is presented with encoded array structure, which has the size of elements inside it and have the references to the same encoded value. So basically, this encoded array is a sequence of other encoded values. Thus, this approach is able to store values of arbitrary type, even the array of integers, whatever it wants. So this kind of flexible structure that keep any value that can be described in Java or Kotlin. And that's how the values stored for the annotations and for the static values section here. And the last, but the most interesting thing here is the offset to class data item structure. It contains the detailed information about this particular class. Let's dive inside it. In essence, class data item describes fields of the class, static and instance fields, and methods of the class, direct or virtual. And fields of the class are defined by a structure called encoded field, which is just a bridge between field descriptor and the access flags. Because field IDX div field point to fields IDs table. And the most interesting thing here that this field is represented as the difference from the index of previous element in the list. The index of the first element in the list is represented directly. That's why we have this div suffix in the naming. Why? Because of saving memory. That's the main idea of to save some space. And again, access flux of the field, public, private field, final, volatile, or etc. So this encoded field structure is just a bridge between field ID, which we discussed previously, and the access flux for it. And almost the same thing we have for encoded method, which actually is a bridge between the method ID and its access flux. But also there is an offset to code item structure which holds the executable code for this particular method. That's the most interesting thing here, because DEX is Dalvik executable. So we finally found where the executable code lives. Let's have a look. Code item. And it's kind of large structure, I would say, but for me it's very interesting. Remember, this talk was made out of curiosity. And let's observe it field by field. As you might know, that Android virtual machine is a register-based machine in opposite to the regular Java virtual machine, which is stack-based. It means that commands executed in this machine take their arguments and put their results in registers, not the stack. And this field sets up the maximum amount of registers which is required to execute this particular piece of code. Also, here we have the number of words of incoming arguments, a number of words of outgoing argument space required by this code, and word term stands for just a couple of bytes. Try item indicates where the code exceptions are caught and how to handle them. We are going to cover it a little bit more later, but what can I say at the moment? That here's how we encode the try catch finally structure in Kotlin and Java. That's for what try item exists. Okay, also we have this debug info item, which contains some debug information about this code. There are a lot of things to cover. Maybe it deserves like dedicated talk about it. So let's skip it for today. Two more fields here, and the size of instruction list in 16-bit code units and instructions itself. This is exactly the place where executable bytecode lives in this file. And at the end of this, we have 2 bytes of optional padding to make the tries section is 4-byte aligned. Okay, and now about the tries. Now it's time to discuss how exceptions are caught in code provided above. Try item has the start address in the block of code covered by this entry. The address is a count of 60-bit code units to the start of the first covered instruction. Also, we have the number of 60-bit code units covered by this entry, how many instructions do we cover, and we have the offset in bytes from the start associated handlers list. This list are also out of scope for today's deep dive because the structures are like also kind of complicated, but I will give you the link to the documentation, and if you're curious, you can discover it by yourself or like come to me, we will discuss it later. Okay, but we skipped part of this handling stuff, but some things need to be mentioned. How the catching exceptions work. Every try item is associated with one or many exception types, which are handled by this particular try item. So, and every try item covers some region of the instruction set. And if an associated exception occurs within this region, when the code is executed, then the handler is invoked. That's how try catch finally works. Okay, let's see the real example. I got this code. Sorry, it's Java, but It's because Kotlin generates a lot of additional stuff, and not to overcomplicate our example, I just write it in Java. Okay, I compile it with Java C and then pass it to the DA tool with debug option, and in the end, I have the class's DEX file. Okay, let's see how strings ID section looks for this file. What can we notice here? First of all, it's the name of the constructor. It doesn't define here explicitly, but as you might know, every class has at least one public no arguments constructor. And this is the name for it. Also, we have in this string table name of the file, because we compiled it with debug option. Also, we have this field and argument name, and also we have the method name here. What about type IDs? Also, we have the integer type here to denote the type of the field and return type of the method. We also have the class itself, fully qualified name. We also have the object, because foo is implicitly derived from object class. We have also string class here, and we have the void, which actually is the return type of the constructor here. So this small class have these 5 entries in type IDs table. Okay, what about prototypes? We have 3 here. First of all, we have, oh, sorry, I think I'm losing microphone. Do you hear me right? Sorry for that. So we have the prototype for the constructor, which is just V, because it have void return type and no arguments. And we have 2 methods, 2 constructors from the foo class and from object class, which refers to this prototype. This is how the duplication works. Actually, we have 2 methods, but they reuse the same structure for prototype. So we save some space for one prototype entity. Also, we have save length method here and the corresponding prototype for it. And we have the length method here with return type int, no arguments, that's it. Also, we have one field here of type integer and name length defined in class foo. And also, we have the class itself here. That's it. Then let's proceed this famous 64K problem in multi-DEX. Raise your hand who remember this kind of errors when you're compiling that application. Oh, a lot of you. So you've been doing Android development so long, right? Oh, sorry. Yes, if you remember this, you've been doing it so long. Okay, what is 64K? Actually, it's the number 65,536, and it can be expressed in 60-bit unsigned integer or use short in our notation. And here we comes to the problem. We can reveal this mystery of 64K problem. Actually, if we have a look at method ID item structure, you might notice that proto IDX field have type use short, meaning that method can reference only 64K prototypes. So actually, one DEX file can contain only 64K unique prototypes. That's what this problem was about. But the problem is that it's not only about your code, but your code with the framework code, with libraries you use, so every prototypes you have in your project are placed here, and why these problems occurs. So how it is solved? If you have the minimum SDK 21, so you have to do nothing because IRT already supports it out of the box, supports multiple DEX files. But if you target Android 19, I mean SDK 19 and below, so you might have already used the multi-DEX library. So what does it do inside? And to avoid this 40K problem, we use this multi-DEX class file and call method install in the very beginning of our application. I have simplified the code to keep the main idea here. And using reflection, this code gets some internal fields of class loader, get value of these fields. And finally, it expands this list with additional items like strings IDs, type IDs, proto IDs, field IDs, etc., which are captured from different secondary DEX files. And this leads us to a key point that 64K problem is just a DEX format problem, not the runtime one. So actually, the Dalvik, even back in the days, can handle more than 64 prototypes and methods, but the limitation lays inside the format of the DEX files itself. So finally, give me like a couple of minutes. Let's compare DEX and jar. Actually, it's not correct to compare DEX and jar because they have different format and they have completely different purposes. And I realized it just after my talk has been announced and I was unable to fix it. But what was my original idea? I wanted to show that both DEX and jar file can contain multiple classes inside. Because DEX designed for it, and jar is just a zip archive which contains multiple classes inside. That's it. That's the only similar thing here. But from engineering point of view, it's more correct to compare structure of DEX and class file. And let's briefly do that. I just copied this from the documentation of Java virtual machine, how the class file looks like from inside. And as you might notice, there is almost the same fields: magic, version, constant pool. DEX have different dedicated tables for the strings, types, prototypes, fields, and methods, while in class file, all these structures are bundled together in one constant pool. And as you might notice, there is also use short here. So technically, class file also have this 64K problem, but for one class, not for the whole application. So I doubt that you would ever reach this limit. Just only if you place all your code inside one file, maybe you can do it. There's also access flags, almost the same that we have in DEX file. Reference to this class, reference to the superclass, just the index in this constant pool, which denotes the type of the superclass. And also we have the interfaces here, which is implemented by this class, and it's just an array of indices in this same constant pool. We have the fields here, we have the methods here, and the structure of this field info and method info almost the same. We also have the access flags here, name, which is indexed in a string, indexed in a constant pool of type string, descriptor and index, etc., etc., etc. So you might notice that DEX file is similar to class file. The only difference not the only, but it contains the many classes instead of class file, which contains only one classes. But it's still not the correct comparison because class files and DEX files are supposed to be used on different virtual machines, register-based and stack-based. So this comparison is kind of artificial. I just wanted to show that engineers who designed DEX files, I believe they were inspired by this class file and its structure. That's my thought. I don't know for sure. I haven't been there, but looks like that format is really similar. And the key thing here is the duplication. So while the class files have their own constant pool, many strings, many types are duplicated many, many times. If you have 100 classes, some strings might be duplicated 100 times. If you have 1,000 classes, some strings might be duplicated 1,000 times. But if you put them all in DEX, this whole 100 strings or 1,000 strings will be compacted in a single one. That's the key idea here, because devices, as a reminder back there in times, was low-end devices with low amount of memory, and so saving these bytes was crucial there back then. What Def uncovered? Actually, I missed these structures, like map lists. We didn't cover too much how notations are stored, how exception catch handlers are stored. We didn't cover the debug information. So if you're interested in these things, you can come to the booth of Bolt. We are here for the whole conference time. We can discuss it. We have a lot of engineers there. We can discuss this stuff. But if you want to read it by yourself, here's the QR code to the official documentation where you can capture all the required information if you are curious enough to do that. OK. How many badgers? 14, right? Yes, this guy was the first. So here we go. Was it easy? Yes? OK. Next time I will make them smaller and semi-transparent, yes, to make this task sophisticated. OK, 14, that's right. And thank you, that's all. Here's the link to my Telegram. You can reach me out there, ask some questions. Also, as I said, you can reach me out to the Bolt booth. We're already here. Came to us. Let's have a conversation. Test drive our scooters and bikes. So we're here for you. Thanks.